Good morning. We are ready to go through some more homework problems. Today what we want to do is we want to look at the later half of chapter 30. That's going to be AC circuits. You can see we're already looking at homework problems with AC power supplies in them. So that tells you we're in the later part of chapter 30, and then as well as all of chapter 31. I know that in the other review I went over 10 minutes. I hope that was okay. I think this one will probably be a little shorter. And then I just want to let you guys know, I'm still trying to decide where the best place to put these review lectures would be, whether it's better to put them right after we've done those chapters or to put them right before the midterm. I'm kind of leaning towards before the midterm, but be ready to see these wherever they show up. They're going to show up as one of the lectures. All right, so with AC power supplies, that's the big deal now, is that we have AC power supplies, and when we hook up a resistor or a capacitor or an inductor, we're going to have some different behavior. Now with a resistor, we actually went through resistors being attached to AC circuits back in chapter 25. We went ahead and outlined how AC electricity works, and we looked at resistors at that time. What's really going to be different for us now are the capacitors and the inductors. And the reason for that is using a phase diagram. The voltage across a capacitor is not proportional to the current. It's proportional to the charge. And when we have charge that is oscillating, and that's what's happening with this capacitor hooked up to the AC, rather than the capacitor never fully charges, right? It charges in one direction, and just when you think it's going to be fully charged, the current reverses and it uncharges, it discharges. It discharges, and then it charges in the opposite direction, but then the current switches, so it's going back and forth, and it could be going back and forth at a pretty good clip. Now in this problem, they gave us a frequency of 660 hertz, which is really fast. So either they intended this to be a really rapid oscillation, or somebody hit the 6 key twice when they were writing up the problem and didn't notice. They meant, standard 60 hertz, but instead it became 660. Anyway, we're going to go with that. Now looking at the voltage here, they also, okay, this is a crazy problem in terms of numbers. This is a 22,000 volt power supply. So it's some kind of a power supply that's operating AC. Maybe there's a transformer. I guess there are things, maybe there are induction systems for spark plugs or something that operate at really high voltages. And so this is at 22,000 volts. And it is oscillating 660 hertz. That's pretty fast. Now, of course, the frequencies, to work with our formulas, you got to be ready to get the frequencies in hertz switched over into radians per second. So we're going to get the omega value, the omega frequency, 4147 radians per second. We've got that. Now, again, we were going through this idea of oscillating current. Well, for the capacitor, let's start with oscillating charge. Take a derivative. That gives us the oscillating current. Now, that means that the charge and the current are out of phase with each other. Now, to represent that, what we showed in lecture was that we could use a phase diagram and imagine these phasors rotating, and that their projections onto the x-axis are giving us instantaneous values. So the magnitude of the current, or the peak value of the current, let's say, or the RMS. Okay, this is RMS. So the RMS value of the current, we're going to say is here. And then the RMS values of the charge, or peak. Conceptually, what's the better way to do this? Everything's proportional. So, yeah, let's try RMS and see where that gets us. So this is the RMS value for the current, and RMS value for Q, and RMS value for the voltage over the capacitor, or peak, either one. They're going to be out of phase, and that's what this is keeping track of for us. And so what we're going to run into here then is that when we go through and solve for the voltage will be out of phase with the current. And so to write out the effect of the capacitor, how much effective resistance does the capacitor have? So in an AC circuit, we're charging and discharging and recharging and discharging. And what we can show is that the capacitor has a certain amount of resistance to it. It limits the amount of current. And when we write out those formulas, what we found was that the resistive effect, what we call capacitive reactance, is given by Vc over I naught, which is given by Q naught over C over Q naught. That's not an I, that's a Q naught times omega. Turns out to be 1 over omega C. And so I've got a certain amount of resistive effect from my capacitor, and that's going to be equal to 1 over omega C. So that's what we're starting off with. They ask us about the capacitive reactance. And that's 1 over omega C, and we've carefully calculated everything here. And so that gives us 2,800 ohms of reactance or resistance. It's kind of an analogous effect. Now, since there's nothing else in the circuit, there's no other resistors, no other inductors, no other capacitors, that one value of 2,800 ohms, that's the total impedance. So not only is the 2,800 ohms telling us the capacitive reactance, it's also telling us the overall impedance for the circuit. It's just got that one device in it. And so what we can do for the RMS current value is take the RMS voltage value, divide it through by the total impedance, and that gives us 7.85 amps. And then finally, to get the peak current, which they ask us for, we can multiply that RMS value by square root of 2. Okay. So I hope you guys have practiced. Back in 25, we looked at a number of examples, practicing going back and forth between RMS and average values, back and forth into peak values. And everything's proportional, which is why this became such a toss-up for me as to which way to think about this. In any case, there's a lot of conceptual stuff going on here. And then once we understand the conceptual stuff, we know which formulas to bring out and how to go about solving the problem. And the calculations aren't all that difficult, okay, in this first example. Now here's another AC circuit. This time we don't have a capacitor, but we have a resistor and an inductor. So if we look at the impedance diagram for this, now this is not voltages and currents, this is a diagram in terms of impedance, and we introduced these in class. These are really handy. I think they're at least as useful as the voltage and current diagrams, maybe more so. They don't get used as much in textbooks. But what we can do is all of the resistances are going to be proportional to the voltages. And so whatever the voltage diagram looks like, we can draw an analogous impedance diagram. So the resistance is here. In a voltage diagram, this would be the voltage over the resistor, this would be the voltage over the inductor, and this would be the voltage over the entire circuit. But here it's resistance, inductive reactance, and impedance. So again, we're paying close attention to the numbers, making sure we're clear on the formulas, and then seeing what we predict. We're operating this at 60 hertz and a VRMS of 120 volts. So this does look like it just plugged into an outlet, in the room here. So plug into one of these outlets, and we're going to get 120 volts RMS and 60 hertz frequency. Now the omega value, the omega frequency will be 377. That's the one we're going to be using in the formulas. And then they tell us the resistance, and they tell us pretty much everything. I'm not sure what's left to calculate in the problem. We will see. this is 965 ohms of resistance, and then 225 millihenries of inductance. Now, I'm sure, oh, I did calculate it. So over here, I got the, we got the inductance, but we really want the inductive reactance. So I got to multiply by omega, and that is going to give us 85 ohms of resistive effect. Now, that says in this particular problem, the impedance, the Z value, is really going to be dominated by the resistor, not by the inductor. I don't know if the person writing this problem intended this, but they've written it where the numbers work out, and that's fine. The numbers work out that we've got relatively a lot of resistance in the resistor compared with the resistive effect, or the reactance, in the inductor. And that means if we draw this diagram to scale, which I haven't, this would need to be, 10, more than 10, 10 or 12 times, 10 or 11 times longer than this side. And that angle is going to be really small. When I calculate the Z value using Pythagorean's theorem from the diagram, I get 969 ohms, which is not so different from 965. Right? But it is different, okay? And in a problem like this, that's an important difference in terms of getting the problem correct, matching the back of the book. All right, 969 ohms total. So again, they just have this list of things they want us to calculate. The IRMS is going to be equal to VRMS over the total impedance. And I've got the 969 over here. That gave me 124 milliamps. Now, you'll notice that I go back and, I use the millis, and I use the micros, and I use the kilo, and those are good prefixes to use. That's pretty standard talking about a lot of this stuff. So rather than using scientific notation, or rather than having 0.0000, go ahead and use those prefixes. Practice using those. Those are good. When I go in and solve the phase angle between the current and the voltage, I get 5 degrees. So if you remember, let's see, I should have written the other diagram on here. This is the voltage across the inductor. This is in the same direction as the voltage across the resistor. This is the total voltage. And the current is lined up with the voltage across the resistor. Those are in phase, but the current is not in phase with the other voltages. Okay. And that's what creates that phase angle between the current and the total voltage. Now, the energy dissipation that they ask about, energy dissipation is only taking place in the resistor, right? Ideally, and we only purchase ideal capacitors and ideal inductors. The inductors and the capacitors are not losing any energy. They do not dissipate any energy. They store energy, but they return it to the circuit. Every cycle we go through, they store some energy, then they return it. They store some energy, they return it back to the circuit. Every cycle we go through the resistor is thermalizing energy, and then thermalizing more energy, and then thermalizing more energy. So that's where the energy dissipation is taking place. Even the power source here can have energy leaving and energy returning, okay, in these kinds of circuits. So the power, now that's not a P to some power, that's just, it's P average, but it's P average for the resistor. So that's just keeping track of the resistor effect. And to get the energy dissipation, that's the only device I have to look at. Don't look at the whole circuit, look at the resistors. And the resistor has resistance R, and it has current, IRMS, and that does get squared. So again, that's not a power, it's not a numerical power. This is power of the resistor, but that's just notation, telling us it's specific for the resistor. So the resistor, on average, is losing energy at the rate of 14.8 joules per second, or 14.8 watts. All right, that's what's going on in the resistor. Now, when we calculate the volt, and again, these are just superscripts, not numerical powers. This is the VRMS for the resistor, and the VRMS for the inductor. I should have put them in parentheses. Maybe that would help highlight that. But the voltages are going to be given by R times IRMS. And since we've got an AC power supply, the voltage across the inductor will be given by the inductive reactance times IRMS. We can use the current, the IRMS, and then multiply by the different resistances to find out the voltages. Now the voltage we have here across the resistor worked out to be 120 volts. I should have kept some more sig figs here because that's not quite true. The 120 volts would be over everything combined. This would be just a little less. You can look at the Z versus the R. That's less than 0.5%, and that's why it's not showing up in the significant figures. And that's why when you're starting out in these homework problems, probably whoever designed the problem, I could have changed some numbers. I guess maybe I should have, so that these were more similar, so you could see the effect. Okay, so the VRMS on the resistor is actually a little less than 120. I should go back and it's going to be 119.5 or something like that. And then the voltage across the inductor is 10. Now you're saying, wait, the voltages don't add up, and then you stop and think, oh yeah, that's right, they're not supposed to. So the way the voltages will work is that we're going to have a voltage diagram, looks just like the impedance diagram. The voltages in the resistor and the inductor are 90 degrees out of phase, and that means we use Pythagorean's theorem. So I can square this, add them together, take a square root, and I will get, where did it go? I will get this. Okay, and again, I should have kept some more significant figures. You guys can do that. Take some more significant figures, see how that is going to work. Ooh, okay, here we go. Now we're going to put everything together. We're going to have an LRC circuit. Now notice everything is in series. And that's pretty much what we looked at. I think in class we set up at one point devices in parallel and talked about them, but we didn't do any real detailed calculations for that. So this is an AC power supply. It's an LRC circuit, and it's all in series. And that's what you want to do when you look at problems. When you look at a homework problem or an exam problem, certainly, even midterm or a problem on the final, find out what power supply you have. Because if you read this problem and you don't have a power supply, it's a very different problem. You know, if you do not have a power supply, that takes you back to the first half of chapter 30, where you were looking at oscillations that gradually die off. And that's not what's happening here. These oscillations are not going to die off. What they're going to do is hit an equilibrium pretty quickly as soon as we turn the circuit on. And any additional energy we're going to need, see there's a resistor that's going to be dissipating energy, right? But that energy will be compensated by the AC power supply. So in this case, it doesn't drop off. The current doesn't decay down to nothing. So watch. If this is an AC power supply, it's this problem. If there's no if there's no power supply at all, it's a problem back in the first half of chapter 30. Okay, now it tells us a lot of stuff. It tells us the inductance, tells us the resistance, tells us the capacitance, tells us the voltage. Everything is known here, right? Yeah, all the values are here. They tell us that we want to operate this at resonance. So we've built this circuit. We have certain values for L, for R, for C, for, well, L, R, and C. Let's leave it at that. And for a particular set of L, R, and C, what we can do is set up what we call resonance. Resonance would say that at a particular frequency, given by XL is equal to XC, we can minimize the overall impedance. So we're trying to get Z to be as small as possible. Now the smallest Z can ever be is equal to R. R is not going away, if I look at my phasor diagrams for impedance, there is nothing to cancel out R. There is something that will cancel out the voltages. Moving down to the voltage, there's nothing that's going to offset the voltage across the resistor. So the resistor will always be in effect, and it's always going to have 25 ohms to it. But there is a way we can get the voltage across the capacitor and the inductor to cancel each other out. Now, they're not losing energy in any case, but what they are doing is they're limiting the amount of current. And if we can get the capacitor and the inductor to have equal voltages, and they're always going to be in opposite direction, then what we can do is get that to go away. And so see what we have here. We found the frequency. So we use this condition to eliminate all of the reactances. And we found the frequency, 1670 radians per second, 265 hertz. If I take this omega value and plug it into my reactance formulas, what I find is I'm getting 50 ohms of resistance of reactance in my inductor, and I'm getting 50 ohms of reactance in my capacitor. So those two devices are getting 50 ohms. The resistor is at 25. These cancel. And so at resonance, the Z value for this circuit will be 25 ohms. And that depended on the frequency. It's just that one frequency at which they'll exactly cancel out. So that says that I can take my VRMS, divide through my Z, which is now just R, 90 volts divided by 25 ohms. That gives me 3.60 amps. So that is, and everything here was in average values and RMS. So 3.6 amps is my RMS current value for that. Let's see, what else did we have to calculate? Oh, so I went ahead, I don't think they asked for this, you can check and see, but I wanted to calculate voltages so we could stare at the numbers. And it said that the peak voltage across the resistor is 90 volts. And I can get, actually these are RMS values. The RMS value across the resistor, 90 volts. The RMS value across the inductor, 180, and the RMS value across the capacitor, also 180. So those 180s are exactly out of phase, 180 degrees out of phase with each other. And from the diagrams or from the sine and cosine functions that we use, we can show those will exactly cancel. Now the power, the rate at which energy is being dissipated in the circuit, again, this always comes back to the resistor. I can take V resistor, I resistor, it's 324 watts. Okay, for the resistor, the current and the voltage will be in phase with each other, and we can still use that straight V times I to get the correct power. With the capacitor and the inductor, we can't use that anymore. We have to average over voltage and current, which are out of phase with each other. And they're 90 degrees out of phase with each other. And that says at least averaged over time, that will work out to be 0. So the capacitors and the inductors, again, they're going to acquire some energy and then release it. They're going to energize and then de-energize, energize, de-energize. The resistor is going to consistently take electrical energy and convert it to thermal energy. All right, let's move on to chapter 31. So that's where we're headed now. Chapter 31 is looking at the propagation of electric and magnetic fields. So I'm going to call this, and I think that's the same thing I did in class in the lectures, propagating electric and magnetic fields. Now, these go by the name of EM waves, and that's fine, I guess, except you have to remember EM waves don't necessarily have to wave. They can. If we have accelerating charges, so the fields that we're talking about in chapter 31 are coming from accelerating charges. The example that we used for that was a radio antenna. saying that in a radio antenna we're oscillating electrons back and forth, current is oscillating back and forth, and that will generate what we call acceleration fields. Now, acceleration electric and magnetic fields are equal to each other in magnitude. The other electric and magnetic fields that we've looked at in past chapters are not. Okay? Those were coming typically from charges that were either at rest or charges at constant velocity. But now we're looking at accelerating charges, generating fields, and the shapes are different. That's, bottom line is, the fields just have a different set of properties. So the picture that we've drawn for this, and that's drawn in the textbook, and that it goes by the name of electromagnetic waves, is it says that at each location in space, there are going to be values for the electric and magnetic field, and those electric and magnetic fields will be at right angles to each other, and they will also be mutually perpendicular to the direction of travel. So compared with and this is light, or some part of the light spectrum, so it's either radio or microwave or infrared or visible or ultraviolet or X-ray or gamma, but they're all considered EM waves. Now they can be wavy, but wavy means that as I step from one point to the next, the value of the electric field varies, maybe like a sine or a cosine function. It's not that anything is, that's not happening. This is not happening. What's happening is we're going from one place to the next, measuring the electric field, and if we assign numbers, we go, oh, the electric field here was 0. Oh, look, it's 5 in the upwards direction. Oh, look, it's 10 in the upwards direction. Oh, look, it's 12. Oh, it's back to 10, it's at 5. Oh, look, it's 0 here. Nothing waved. It was just a series of values that had a certain change to it. And then if we continue farther along, we'll see electric fields oriented in the opposite direction. But again, nothing following that wavy path, just a series of values that when we write them all down can be represented by, the values can be represented by a sine or a cosine function. Okay. All right. Now in this, what they told us then, they gave us they said we've got an electromagnetic or an EM wave propagating electric and magnetic field. The magnetic field components are measured to be RMS values 12.5 nano Tesla. Now, as long as we're in the point now where these accelerating fields are what we're looking at, let's just use E and CB. So that will put the electric and the magnetic field components on equal footing. And if I multiply V times C, I'm going to get the magnetic field in terms of newtons per coulomb, and it turns out to be 3.75. Well, the electric field then will have the same value, 3.75 newtons per coulomb. So all components of the electric and magnetic field have the same, or the electric portion and the magnetic portion have the same magnitude in these acceleration fields. All right, in problem 23, we're looking at energy transport. So another feature of these acceleration fields is that they actually carry energy away from the source. The electric and magnetic fields that we were looking at back in earlier chapters, up through chapter 28, where the charges were at rest or the charges were at constant velocity, they had fields that we could identify surrounding those charges, and the effects had a delay, a time delay to them, which means, oscillating a charge here, a charge farther away won't feel that effect for a while. But if they were moving at constant velocity or at rest, they weren't transporting energy away. And now we're looking at a situation where these EM waves are actually carrying energy with them. So in problem 23, they've got this cubic centimeter area. Now I got that converted into cubic square meters, not cubic, square. Square centimeters into square meters. and make sure you get the conversions correct here. That's 2 powers of 100 we have to keep track of. And then let's just go through all the stuff we talked about in class. They gave us a starting point by telling us what the magnetic field is. Hey, if they give me one piece of information, I can kind of fill in the rest. Now, these are B's, they're not 13s. They're B's, right? Yeah. So that's a B. I recognize it. I'm just hoping you guys are used to my handwriting. 22.5 nanoteslas. When I took a factor of C and multiplied, I got 6.75 newtons per coulomb. Well, that tells me the electric field will have the same magnitude. So now I know that the magnetic field and the electric field, same magnitude, and I can move on from the field and calculate the energy densities. And that's because it's an energy question. I've got to get the energy densities calculated, which I did. I followed the formulas. E squared and then CV squared. They both have the same coefficients out front. So not only do the fields match, but the field energy densities match. And so the total energy density comes from adding these two together. So they each have an energy density of 2.0, 10 to the minus 10 joules per cubic meter, and that's a pretty tiny number. Now to get the intensity, and this is something that we had derived back in class, I take the energy densities, combine them, multiply by C, and it turns out that this EM wave, this propagating electromagnetic field, has an intensity of 0.121 joules per second per square meter. Square meter. Which is the same thing as watts per square meter, which I hope, we've seen intensity in a number of different situations at this point. We saw it way back with sound, I guess was the first introduction in Physics 4a, and now we've seen it a few times here in Physics 4b. Well, if this is intensity, what I can do is I can calculate the energy, and I've used U here so it doesn't get mixed up with E for electric field. So the energy is going to be the intensity. That's not current, that's intensity. Oh no, we don't have enough letters. Okay, the I's here are intensity, not current. The E's here are electric field, which I hope is you guys are assimilated with that now. So U is equal to the intensity, not current, times the area times the time. That's kind of doing intensity in reverse. So the energy that they wanted was 335 joules. Now 335 joules doesn't sound like a tall order. That seems easy enough, except that the intensity of the light coming in, whatever part of the spectrum it's in, the intensity of light coming in is not very much. So I divided through by that intensity and divided through, and the area is not much. This is per, square meter in front of me. So I got this coming in. I'm only getting 0.121 joules per square meter per second, and the size of our target is only a square centimeter. Okay, so that's going to be 1/10,000th in terms of the size. The square meters are really tiny. Well, I calculated 27 million or 28 million seconds, which I thought I should convert into days. I should have boxed this one. 320 days. So it's gonna take a while to accumulate 335 joules from this perfectly absorbing. Did I write that down? In the problem, they said it was perfectly absorbing something. It's going to take a long time to accumulate 335 joules. So just, an aside here, if you get an answer like this on a problem like this, don't leave it in seconds. Nobody wants to see millions of seconds as your answer. Put it into something that people can see and it immediately makes sense to them. If somebody says, oh, that's going to take 27 million seconds, what's your first thought? And you're thinking, gosh, how long is 27 million seconds? If somebody says 320 days, done, right? Then you go, oh, 327 days. Yeah, I know what that, 320 days. I know what that is. Okay, so that's the idea. So make your units, your time units make sense, is what I'm saying, what I'm suggesting. All right, I think we got a couple more examples here, and then I think we're on course. In problem 25, we're going to redo kind of everything we did in the last problem, except this time, instead of having the light in kind of a beam approach, a beam geometry, we're going to have it in a spherical, spreading out shape. So it tells us that we have a central source for our light, for the EM propagating field. So we have a 1500 watt light source. Now again, that doesn't have to be visible light. It can be any part of the spectrum: radio, microwave, infrared, visible, UV, X-ray, gamma. I hope it's not one of those really energetic ones. Those sound dangerous. But let's say we have a 1500 watt light source here, and we want to step away from that by 5 meters. Now at a 5 meter distance, what will the intensity be? So here's another chance to think about intensity. Don't just plug numbers into a formula. Stop and think what they're telling you. So if I'm standing at this distance, how intense is the light? And I did a spherical surface area. This is going to be 4.78 watts per square meter. So that's the rate at which energy is going to be coming by along that surface 5 meters away every second. Okay, so that's how many joules per second. Now, we can kind of go backwards through the formulas. We've been starting with fields and calculating intensity. This time we're going to start with intensity and work back and calculate the fields. So you just want to run the equations in the opposite direction. So to get the total energy density, I can take I over C. That gave me 1.59, 10 to the minus 8 joules per cubic meter, and I wrote that down, energy density. Now, the bookkeeping that we do with energy density is half of it gets assigned to the electric components, and that's because of the way the electric and magnetic fields are. Half goes each way. So I'm going to get half of that in the electric fields and half of that in the magnetic fields, so I divided by 2. And then I calculated the fields, E and CB, and I don't know, there's something satisfying or reassuring, I guess, to see those side-by-side calculations. So the fields did work out to each be 42.4 newtons per coulomb. Now, at the end of the day, I figured I better put Tesla in there, because who knows going to be grading my paper, and maybe they're going to want to see Tesla. And so I did put Tesla in. You know, I lean towards putting the newtons per coulomb in there. I think is really handy to be able to compare electric and magnetic fields on an equal footing. But yeah, at the end of the day, definitely put it in Tesla also. Now, everything in the problem here was done implicitly in terms of averages and RMS. And that's because if you read the problem, it says a power source of 1500 watts. And the default is the average. So that's what everything is done in terms of for this. Finally, I guess, here is our last problem. And this was kind of a fun example. We did one similar to this in lecture. What we're going to do is take a beam of light and use that to push around a tiny, tiny object. So we've got this small object. They say it's shaped like a cylinder. They say that its radius is 500 nanometers and its length or height or whatever h is 500 nanometers. For a cylinder, the volume would be pi r squared h. There's the volume, 10 to the minus 19 cubic meters. This is a really tiny, you can't see it. This is the size of hundreds of nanometers. Okay, so you know, half of a micron, and what is it? Red blood cells are 3 microns across or something, and you can't see red blood cells. So this is really small. And then they say it's made out of a material that has the density of water. So I don't know, is it like a little piece of ice or something? It's fairly low density. I could imagine if it was a little granule of silicon dioxide or something, little granules of sand, the density might be, you know, 2 or 3 times that amount. In any case, with that density and this volume, it turns out this object has a mass of about 4 times 10 to the minus 16 kilograms. Now the reason we want mass is that they want us to find out how much acceleration can we get if we shine some light on this object. This object's just sitting there, and we're going to hit it with some light. It says this object, now it says this too, it says that this object is 100% absorbing, which makes me really nervous. Because if we hit it with a powerful light beam and it absorbs all that energy, we could vaporize this, okay? And so that's something to keep in mind. If you've got these little tiny structures and they're 100% absorbing, and you hit it with something really powerful for a period of time, you could vaporize the material. It could heat up and not be able to dissipate the heat rapidly enough. I think that's a risk here with the numbers that we're given. Anyway, this is a really small mass. Here is the light coming in. Now this is serious. I mean, this is 1 watt. And this is an object we can't even see. It's much, much smaller than anything we could see. The cross-sectional area that's absorbing this is, well, I calculated that at 7.9, 10 to the minus 13 square meters. That says the intensity of the light hitting this little tiny object is 1.3 trillion watts per square meter. Now, there's not a trillion joules around, but the energy coming in is only 1 joule per second, but it's really, really concentrated. And so as far as the intensity, you wouldn't survive that intensity of light. This little tiny thing's not going to survive 1 trillion watts per square meter. This is much higher than the intensity of, I'm going to guess, I should be careful. It's got to be comparable to the intensity of light coming off the surface of the sun. I don't know. We should do a comparison and find out. That's a really high intensity. Now it says it's all absorbed, and we're going to use the formula that we had derived in class, power divided by c, and it tells us that the force then that this little tiny object will experience, it's 10 to the minus 9 newtons. Now you're thinking, how can that intensity of light create that small force? Well, it's not much surface area. So even though the light is extremely intense, we have to think more in terms of 1 watt coming in, 1 joule per second, and that 1 joule per second of light is going to produce 3 nanonewtons of force, which is not very much force. Now the acceleration we're going to get, though, notice that what we have is 10 to the minus 9 newtons and 10 to the minus 16 kilograms of mass, and we're getting an acceleration that's in the millions of meters per second squared. Okay, so it's gonna have enough. This is gonna be noticeable. This is not a small effect that we've got here. We really blasted this little tiny particle of whatever that we had. All right. Okay, so if the objects are small enough, light becomes important. I think one of the examples that we talked about in class 2 was that during the formation of the solar system, there's a gravitational collapse into different objects. Once the sun, once the central star, the core becomes high enough temperature and it ignites fusion reactions and it heats up, all of that light that's generated begins to push all of the remaining little particles of what we call dust, little particles out of the star system by a process similar to this. So light really can, if all you've got is a collection of little tiny particles, light can easily push those particles around and clear the solar system of the remaining dust. Okay. All right, that's a good place to stop. I guess we finished our review for 30 and 31. So we'll stop there. If you guys have questions, stop by office hours. All right, promise? Okay. All right, we will stop there for the day.